Okay, let's talk ground reaction forces. The ground reaction force is the force of the ground pushing on an object. All right, I know that seems obvious, but it's important to define it. The ground reaction force is in reaction to the object pushing on the ground. And we know from Newton's second law, we add up all the forces acting on the object and we understand the object's, in this case mass, acceleration of the center of mass. So Newton's second law, we only identify the forces acting on the object, not by the object. And we put all those forces acting on the object into this equation. So our kinetic analysis, we have to spend some time practicing using this equation, which is simple, but the trick is to always just put forces acting on the object into this equation, not by the object. Even though there's times, and you'll see in these presentations, how we want to sometimes understand the force created by the object, in this case by the person, but in order to do that, in order to understand that force, we actually analyze the reaction forces. Okay, the ground reaction force is a three-dimensional force, meaning there's three dimensions to it. And when we're in the biomechanics lab, we will typically use these descriptors to describe each dimension. The anterior posterior ground reaction force, the medial lateral ground reaction force, and the vertical. Now, oddly enough, depending on which lab you're in across the country or across the world, you may call this X, you may call this Y. Sometimes labs call this Z. And so it gets a little confusing. And even in our lab, we do switch between what letter we use to represent each of these axes. So it's always important to define which letter goes with which axis. But you can never be wrong by using the descriptors anterior, posterior, medial, lateral, and vertical dimensions. I'll put down that we typically in our lab call this X, we typically call this Y, and we typically call this Z. Okay, now in a physics class, you may call vertical Y, you may call this X, and you may call that, that Z. The letter doesn't really matter. What matters is communicating what dimension we're actually talking about, and that each of these axes are 90 degrees from each other. That is, they're orthogonal. So that's our Cartesian system, where each of these axes are 90 degrees. So we'd have an X. Oh, I just did it mixed up based upon how I just described it. X, Y, and Z, something like that. Okay, and those three axes are 90 degrees to each other. And what we'll do is we'll analyze the ground reaction force one dimension at a time, typically. Now, as we get further in understanding human performance, we may want to analyze a combination of these axes, and so we start calculating what's called the resultant ground reaction force. And the resultant ground reaction force would simply be using Pythagorean theorem to add up the forces at in each dimension. So the square root of x squared plus y squared plus z squared would give us the resultant ground reaction force. Now, sometimes we do the resultant in the horizontal plane. Both of these are horizontal, anterior, posterior, medial, lateral. Or sometimes we'll do the resultant in the sagittal plane. So we would take the anterior, posterior, and the y, and the z, the vertical dimensions. And sometimes in the frontal plane, where we would take the vertical and the medial lateral ground reaction forces and calculate the resultants of those. In that case, if we did the resultant for sagittal, for example, we would do the square root of, and I'm going to write this out, vertical squared plus anterior posterior dimension squared. That's what that would look like. Okay. So, but most of the times in this class in 346, we're going to do one dimension at a time. One dimension. So we'll look only at the anterior posterior ground reaction force component. We'll look only at the medial lateral or only at the vertical. And most of the examples I use to get started are vertical, and then I go into anterior posterior a little bit, and I don't really touch medial lateral for human movement at this stage because medial lateral is a pretty unique force, especially during tasks like running or walking. Becomes more a factor when we start talking about changing direction, like cutting maneuvers. Then that becomes a really important component to look at. Okay, so that's some nuts and bolts of ground reaction force. What I want to do now is apply the ground reaction force to some really simple situations. So let's start with projectile motion. All right, a projectile is when an object is in the air and the only force acting on it is gravity. And so I'm not going to concern myself with air resistance at this point. Air resistance is a force, that's drag force. But at this point, just for sake of discussing this, at this stage for setting up the ground reaction force, we're not going to concern ourselves with air resistance. All right, so if we look at a free body diagram, I've got my object in the air. All right, it's not touching anything. And the only force acting on the object is the force of gravity. Okay, that's the force that we need to put into our equation. Some of the forces acting on the object is equal to the product of mass of the object and the acceleration of the center of mass of the object. Okay, that's it. So our kinetic analysis, we've identified the only force acting on the object because we're not dealing with air resistance. Therefore, I'm going to put that force into this equation, and we always are doing up is positive. That's standard, and we don't need to flip that in any direction. There are times where a physics book or even biomechanics will flip to up is up is negative or down is positive. We're not going to do that. Up is negative works for all the discussions that we're going to have. So negative, indicating the direction of the vector, is downwards. Mass, which is the measure of inertia of the object. Acceleration of the center mass. Now we know for projectile, acceleration is going to be negative 9.8 meters per second squared. Well, if you look at this, we can calculate acceleration of the center mass by moving m over here, fg divided by m. And here's the funny thing about the force of gravity, is that the magnitude of the force of gravity will always be adjusted based upon the mass of the object so that the acceleration of the object is negative 9.8 meters per second squared. That's really odd, but that's what happens. So what does this tell us? If gravity is the only force acting on the object, no air resistance, no matter what mass object we drop, that object will accelerate negative 9.8 meters per second squared. So it doesn't matter if this is a bowling ball, a tennis ball, a ping pong ball, a beach ball, as long as there's no other forces acting on the object, this object will accelerate negative 9.8 meters per second squared. The reason why a beach ball may fall at a slower rate than a bowling ball in real life is because air resistance is a real force, and that would be creating another force acting on the object, and that force would have to be put into this equation, which we're not going to do right now because I'm saying no air resistance. So this is a simple example of setting up why we use the force of gravity being negative 9.8 meters per second squared using our kinetic analysis. Okay, one force acting on the object, and we know that this object will accelerate negative 9.8 meters per second squared. And if we go back to some of our kinematic information on projectiles, you'll see that, and this is the kinetics that supports that. Now, what we don't know is why the force of gravity adjusts based on mass so that the acceleration is always negative 9.8 meters per second squared. We don't know that. I don't know it. There's some good theories out there, but right now we don't have a full understanding of that. And I say we, meaning the science community in general. There's lots of neat ideas But right now, for the purpose of this discussion, is we know the object will accelerate negative 9.8 meters per second squared if the force of gravity is the only force acting on the object. And our kinetic equation, Newton's second law, works to explain that. All right, now let's do a little bit more complicated situation. We'll do a box sitting on the ground and not moving. Oh, yeah, not that exciting because we want to get to human movement, but this is non-movement examples. Well, what forces are acting on the object? Well, we've got two forces now. The force of gravity pulling down on the object, and the object is in contact with the surface, and therefore there's a ground reaction force. That table, in this case, that ground is pushing up on the box. Now the box is not moving. This is critical because we're going to deal with movement in a little bit. But let's stick with our kinetic analysis. We identified forces acting on the object, not by the object, but on the object. Gravity is pulling down on the object, and the table or the floor or the ground is pushing up on the object. Those are forces acting on the object. Neither of these are the by, okay? We are not identifying or talking about by forces. Now, eventually we will, but for kinetic analysis, we don't. So at this point, I'm really, even though it's obvious, I'm going to say I'm dealing with vertical dimension right here. And what I do is I add up the forces acting on the object in the vertical dimension. Up is positive, and that's always going to be the case for anything I do. And we put those forces into this equation. FGRF plus negative, indicating it's a downward force, gravity force, equals the product of mass of the object and the acceleration of the center mass. Okay, that's our kinetic analysis. That's our two forces acting on the object. Okay, now remember, this object's not moving, so velocity is zero. It's 0, 0, 0, 0. It's constant and zero. Well, when you remember, when you have velocity that is constant, and in this case it's zero, then the acceleration, therefore, the acceleration is 0 meters per second squared. Look what happens to the right side of the equality sign. This product turns to 0. Therefore, I can rewrite that equation as the ground reaction force is equal to the force of gravity. The ground reaction force is equal to the force of gravity. So we actually just weighed the object. Okay, that's what we did. And that's how we do this. That's how we weigh an object. We put it on a scale and we don't let the object move. And then we measure the ground reaction force, and that tells us what the force of gravity is. Okay, they're going to be equal to each other when, this is really, really important, when acceleration is 0, acceleration of the center mass. If the acceleration of center mass is not 0, then this situation is not true. This is only true when the acceleration of the object is 0. Okay, so let's look at doing this exactly. Let's say you're going to stand on the bathroom scale to weigh yourself. Let's see why that tells you your body weight. So here's standing still. Here's the person, just a little stick figure. What forces are acting on the object? This is really important. The force of gravity pulling down on the person, and the force of the ground pushing back up on the person. Now notice I didn't say what forces are created by the person, okay? Yes, the muscles are contracting and pushing on the ground. The ground reaction force is in reaction to what the person's doing while standing there. So we're not going to put those forces created by the person into our kinetic analysis equation. Instead, we're only going to identify forces acting on the object. And these are the two forces. And again, we're dealing with vertical dimension here, force of gravity, ground reaction force in the vertical direction. And then we put those forces into this equation. Add up all the forces acting on the object equals MACOM, center of mass. Ground reaction force, up is positive, so this ground reaction force is going to be positive, minus FG, because FG is pointing downwards. Standing still, so velocity is constant. A is therefore 0. If we do final, remember A is rate of change of velocity, so final velocity is 0, initial velocity is 0 meters per second, divided by any time, acceleration will be 0. Velocity is constant. Remember, a 0 acceleration only means velocity is constant. Doesn't necessarily mean the person's standing still. It means velocity is constant. Therefore, I put that A up here. That wipes out the right-hand side of the equality sign. And FGRF will be equal to FG. So in this case, this ground reaction force is telling me what my body weight is. In order to get an accurate body weight measurement, you have to be standing still on the scale. If you are moving up and down, if you're swaying in any case, the velocity of the center of mass will not be constant and it will not be 0. Therefore, acceleration will not be 0. And there's a product here that we have to account for. And those two forces will add up to whatever the acceleration is times the mass. But stand still when you're trying to measure body weight on the scale, and you'll be able to get an accurate measure. And you can do this. You can stand on your scale. If you start, moving up and down a little bit, you will you will see the scale fluctuate. The scale is going to fluctuate because there's acceleration happening, and these two forces adjust based upon the acceleration. Well, it's actually the other way around. These two forces cause the acceleration. All right. And so, but there's an equality sign there, so they all have to match up. So this is not Newton's third law. This is not. Yes, these two forces are equal in magnitude and they're opposite in direction, but that is not Newton's third law. These are forces acting on the object. Newton says in his third law, for every force acting on the object, there's an equal and opposite force created by the object, or vice versa. That's a whole different situation if we want to include or talk about the bi-forces. But this setup is only identifying forces acting on the object, and we put those forces acting on the object into this equation. There are times, and we'll see it in the next video, where ground reaction force is not equal to the force of gravity, and therefore we have acceleration. So this force, the ground reaction force, is in reaction to what the person's doing, and we can fire our muscles. We can push on the ground with different amounts of force, which will cause an acceleration. So this setup, this equation, is not Newton's third law. Newton's third law says for every force created by the object, there's an equal and opposite force acting on the object. To use Newton's second law, we only use the forces acting on the object and put them into this equation. And we leave the bi-forces behind. Okay, the next video that you'll watch will be dealing with some movement, and we'll get away from standing still. Okay, thanks.